we will begin the next module. Okay, module 4 is complex integration. Cauchy integral theorem and Cauchy's integral formula. Here is a definition. A curve C that is got by joining finitely many smooth curves end to end is called a contour. So contour is nothing but a curve. Okay, it is a curve that is obtained by joining finitely many curves. We can join many curves and we can obtain a single curve. That curve is named as contour. Let C1, C2, Cn be denoted, be the n smooth curves such that the terminal points of the curve Ck coincide with the initial points of Ck plus 1. For k is equal to 1, 2, etc. n minus 1. We can express the contour C by C is equal to C1, C2 plus etc. plus Cn. So this is nothing but joining all the curves. So the end will be connected. That's what I mentioned here. The terminal point of the one of the curve will be connected to the initial point of the next curve. Ck coincide with initial point of Ck plus 1. So all the curves will be joined finitely to form a new curve that is called as contour. Next definition, a domain D is said to be simply connected domain if every closed curve C contained in D can be shrunk to a point without passing out of the domain D, and otherwise it is said to be multiply connected domain. A multiply connected region can be converted into a simply connected region by introducing one or more strips. So here, this region, first region, this is simply connected domain. Okay, this, let us consider this domain and this is simply connected. If you draw any closed curve, if you draw any closed curve, all the points will be inside this domain only. Okay, so here it is multiply connected because if you draw some curve here, it has, you see, some of the points it lies outside. So these points are not included in this domain. Points of this particular region and this particular region is not included. So we say this is multiply connected. Also, multiply connected domain converted to simply connected domain. Okay, so if you take some strips like this, it seems to be simply connected. Okay, so all this region like this, it comes under one domain. So it can be converted to multiply connected, converted to a simply connected. So this is simply connected and this is multiply connected domain. So now Cauchy theorem, we'll learn Cauchy theorem. If f of z is analytic in a simply connected domain D, then for every contour C in D, integral over C f of z dz equal to 0. So we take a simply connected domain which we learned now. Okay, some region that is simply connected, and in that region we define a function f of z, and if f of z is analytic in that region, then for every contour C, contour means the curve C, if you take any curve, any closed curve in that domain, okay, so this is closed curve, so we have taken the integral like this. For any closed curve along that curve, if you integrate f of z dz, the answer will be 0. Integral f of z dz is equal to 0. So what does Cauchy theorem say? If f of z is analytic in a simply connected domain D, then for every contour C, for every closed curve C, if you find the integral over that, integral over C f of z dz is equal to 0. So next, independence of path. If f of z is analytic in a simply connected domain D, then integral of f of z is independent of the path in the domain. So it does not depend on, if f of z is analytic, then the integral of this f of z does not depend on the path in the D. Now Cauchy integral formula, let f of z be an analytic function inside and on a simple closed contour C, taken in the positive sense. Okay, closed contour C taken in the positive sense. If A is a point interior to C, then f of a is equal to 1 by 2 pi I integral c f of z dz by z minus a. Let f of z be analytic function. We take analytic function and this is analytic inside and on a simple closed curve C. Okay. So if f of z is analytic and the contour here is C and A is a point inside the contour, then we can define integral over C f of z by z minus a dz is equal to 2 pi I into f of a if a lies inside C, 0 if a lies outside C. So if you take any contour, okay, this is the contour or the closed domain, okay, closed domain C, and for any element or any point A inside this, and we can take f of z to be analytic, okay, f of z is analytic inside and on the closed curve C, okay, f of z is analytic function, f of z is analytic function inside this curve and on this curve. A is any point here, okay, A is any point here, and you take some direction like this, and Cauchy integral formula says that integral over C f of z by z minus a dz is 2 pi I f of a if a lies inside C. So if this particular a value is any point inside the curve C, then you can take 2 pi I into f of a as the answer. And if this particular point A lies outside this curve C, then the value is 0. Okay. So now let us do problems using Cauchy integral formula and Cauchy theorem. What does Cauchy theorem says? Cauchy theorem says if f of z is, just now we learned Cauchy theorem also. Cauchy theorem says if f of z is analytic inside and on a simple closed curve C, then integral over C f of z dz equal to 0. Okay, Cauchy theorem says that if f of z is analytic inside and on the closed curve C, then integral over C f of z dz is equal to 0. So it is enough you find whether f of z is analytic inside and on the closed curve C, then integral value is 0. If you apply Cauchy integral formula, which is important, you can find out whether A lies inside the curve C or A lies outside the curve C, and whether f of z is analytic. And we can say if it lies inside, if this particular A value lies inside the curve C, then solution is 2 pi I f of a. If it lies outside, then solution is 0. Then we go to the problem session. If C is the unit circle, mod z is equal to 1, show that integral over C f of z dz equal to 0, where f of z is equal to e raised to z sin z. F of z is e raised to z sin z. So we know what is analytic, and we have proved certain functions are analytic. So it is enough we write, we know that, okay, we know that e raised to exponential function e raised to z is analytic. It satisfies CR equation and it is differentiable, and hence it is analytic. We have proved this earlier. Okay, we have proved this in complex differentiation. E power z is analytic. Also we have proved sin z is analytic. Okay, sin z is an analytic function. So product of two analytic function is analytic. E power z sin z is analytic inside and on the curve C. Okay, where C is the unit circle, mod z equal to 1. You know, unit circle means circle with center 0 and radius 1. Okay, unit circle means actually unit circle means a circle with radius 1. Okay, here center 0 because it is mentioned like this, modulus of z is equal to 1. So mod z equal to 1 represents a circle. Okay, modulus z equal to 1 is a circle. Okay, circle with radius 1. So e power z is analytic inside and on this curve C. So this is the curve C. It is analytic inside and on the curve C. So what does Cauchy theorem says? Cauchy theorem says if f of z is analytic inside and on a closed curve C, then integral over C f of z dz is equal to 0. Here unit circle is closed curve, right? Here C is a circle, so it is a closed curve and it is analytic inside and on the curve C. So we say integral over C. So this is f of z. What is f of z? E power z sin z. Therefore, by Cauchy theorem, integral over C f of z dz is equal to 0. Okay, integral over C f of z d is equal to 0 using this theorem, since f of z is analytic. Hence we have proved what is that? We have showed that integral C f of z dz equal to 0. Okay, next question you see, evaluate integral over C e power 2z dz by z plus 3 into z plus 2 where C is the circle mod z equal to 1. So here also we assume this particular function as f of z, okay. F of z equal to e power 2z by z plus 3 into z plus 2 is analytic inside and on C, okay. Inside this curve, this particular function is analytic. We know exponential function is analytic. All polynomials are analytic. E power is an exponential function. This is analytic. And z plus 3, z plus 2 polynomial is analytic. We say this whole function is analytic except at the point z equal to minus 3 and z equal to minus 2. Because when you take z as minus 3, what happens to the denominator? Minus 3 plus 3? 0. 0 into any number? 0. So e power 2z by 0 is infinity, undefined, okay. So when you take z as minus 2 also, you get minus 2 plus 2, 0. Denominator becomes 0, any number by 0, infinity. So at this particular points, that is minus 3 and minus 2, this function is not analytic in all the other points. But minus 3 and minus 2 lies outside the curve C, okay. We will draw the circle. If you draw a unit circle, what will be the radius of unit circle? Radius will be 1, right? Unit circle, therefore this particular point will be 1. This particular point will be minus 1 because mod z equal to 1 is a circle with radius 1. So now these two end points are 1 and minus 1. What about minus 3? Minus 3 lies somewhere outside, right? Minus 3 is here, minus 2 will be here. So both these points lies outside the circle C. Okay, z is equal to minus 2, z is equal to minus 3 lies outside C. 0 lies inside C. Okay, so we have to identify whether the point lies outside C. So this particular point lies outside C. So f of z is analytic. At this particular point, f of z is not analytic. F of z is not analytic at this particular point. So you don't get confused. You have to say at the point for which the denominator becomes 0 lies outside. So here if you see at z equal to minus 3 and minus 2, this point lies outside C. So f of z is analytic inside. For every point inside C, f of z is analytic. What is Cauchy theorem? Cauchy theorem says that f of z should be analytic inside and on C. So don't worry about the points outside C. Okay, f of z is analytic inside. So that is the conclusion here. So since f of z is analytic inside and on C, by Cauchy fundamental theorem, we say integral over C f of z dz equal to 0. So what is our solution? F of z. Our solution is integral over C f of z dz equal to 0. But what is our assumption? F of z is e power 2z by z plus 3 into z plus 2. By Cauchy theorem, so this particular integral value is equal to 0. Hence we have evaluated the value of the integral. This is our solution. Okay. So first you have to verify whether the given function is analytic. Okay. Then you can use Cauchy theorem. If it is analytic inside all the points, if it is analytic inside and on the boundary, then we say by Cauchy theorem value is equal to 0. So this is the solution.